Thank you for inviting me today. I am proud and daunted to be here speaking in front of so much brain power. But anyway, I'll get into the juicy stuff quite soon. Of course, you guessed it, it's electrical machines. First, I'll just zoom out a little bit and talk about some of the challenges that are ahead of us in the aviation industry and that Rolls-Royce is working hard to address. We know that 24% of greenhouse gases emissions globally are coming from transportation, and approximately 2.7% are from aviation and combustion of jet fuel. We also think that the air traffic will grow at a rate of approximately 4 to 5% each year in the coming years up to 2050. So that is the upper curve here. The lower curve is the ambition set by the European Commission to reduce CO2 emissions by 75% within 2050. And this is creating a quite large gap between the sort of the ambition and the no action scenario. So we think that some of this will be covered by existing technologies and improvements of those, and quite a large bunch of that also needs to come from new technologies and more radical innovations. And I think electrification will be part of that equation, and of course then electrical machines. So I am here today representing Rolls-Royce Electrical Norway. We were once a startup and are now a proud member of the Rolls-Royce group and Rolls-Royce Electrical. We are situated in Trondheim and are focusing, and have always focused on custom design of permanent magnet machines with the drives and controls. We are set up to be a prototype accelerator and really a fast maker of prototypes. And we sort of say to ourselves that we can custom design everything from grid to shaft. Today I'll focus on electrical machines, as this is what we're using COMSOL for, and since this is a COMSOL conference. So this graph is showing some of the machines that have been designed and built and tested by Rolls-Royce Electrical Norway. And the purpose of this is sort of just to see, you see it's a logarithmic scale, and it's showing that it's a lot of different designs. So we can't really rely on just sort of tweaking the last machine we made. We actually, in many cases, have to rely heavily on our calculations to be correct. So today I'm going to actually take you through a bit of the design process that we do for electrical machines using COMSOL. And you see here the scales are speed and torque. And that is important, because if there's one thing that I want you to take away from this session, and what you have learned in this, is that for electrical machines, it is actually the torque that is dictating the size and the cost of electrical machines. It's not the power. We often talk about the power because it's what we, in many cases, want. It's what is giving the customer utility. But the power is actually the product of rotational speed times torque, or angular velocity times torque. And I have an example here. These are two machines that we have built, a marine propulsor and a winch, both with similar power rating, one 56 kilowatt and the other 55 kilowatt. But one is running at 4,000 RPM, while the other is running at 74 RPM. And one has then 130 Newton meter in torque, while the other has 7,000. And the result is that one machine is like this big, so you can lift it with your hands and put it on the table, while the other one is almost a meter in diameter and requires cranes and jigs to sort of handle it. Same power rating. Going into a bit of design process, we usually then start with our a self-made MATLAB script called the Smart Tool, running analytical calculations based on Maxwell equations and things like that. So we have optimized that to take sort of customer requirements like voltage, rough dimensions, well, speed, torque, stuff like this. We input that, and then we get quite soon to one very important input, which is heat management. So the second most important thing with regards to the size of the machine is actually your ability to get rid of heat. So in the early stages, we just sort of have some empirical data on what we think we can load the machine with of current, and we use that, and through Smart Tool we can do some Pareto optimization, and then we pick our machine and we make Smart Tool set up the geometry and send that to COMSOL, and then we do more detailed calculations in COMSOL. Then we start getting well, detailed answers for voltage and current and stuff like this, and also losses, which are creating the heat. Losses are coming from eddy currents and hysteresis in the rotor and the stator. We feed that loss information again into a thermal calculation, where we in the end get a temperature. And then here everything depends on everything. So actually we then see that based on the temperature, the magnets will, for example, with increasing temperature, reduce its strength, or the conductivity of copper would also be lower with higher temperature. So we run this calculation again till we're happy. So that's the rough dimensioning. We also depending on the application, actually, we do different sorts of detailed calculations. So we do short circuit calculations. We can calculate the electrical stresses on the insulation, magnet losses, winding copper or AC copper losses. More detailed CFD analysis. We can calculate the attraction forces between the rotor and stator. So when you try to introduce the rotor into the stator, it will actually try to suck itself in. So you need to know how big those forces are. We do vibration and noise calculations and the temperature distribution as mentioned. And I guess a dream of the future is to have more and more of these models coupled together in one big thing, and maybe even one day run some sort of live data into that. But at the moment, that's still a bit into the future. We are coupling some of the models already. So for the thermal analysis, we couple the CFD module with the heat transfer module, for example, to get a better precision. And then we also rely on this inbuilt sensitivity analysis in COMSOL, which is very, very important to us actually, because the temperature in the machine is quite heavily relying on some of the input values, which can be uncertain due to manufacturing, for example. So we use that to identify what are the bottlenecks in our heat management system and try to figure out where we should put our focus. We also do some other stuff. Here you can see a marine propulsion machine that has a very low vibration and noise signature. But to actually know that it's reduced to its minimum, we need to do some quite detailed calculations. And what we've done here is to first calculate the electromagnetic excitation or the force put onto the stator from the rotor, and then see the mechanical response actually from the electromagnetics. And for a smaller scale, this has all been connected also into one big model. What we're seeing here is that it's actually quite good correlation between the measured and the calculated results. So this is for the actual machine after it has been tested. Something that we have done a bit of lately, so this is quite new to us, is three-dimensional skewing of the magnets. Segmenting the magnets is quite common to reduce eddy currents in permanent magnet machines. What is new is that we can now calculate this in a much more precise way. So we can skew the magnet segments and actually calculate the reduced total harmonic distortion in the induced voltage, and also the reduced cogging torque due to this skewing. And then I'm coming to one example of, I mentioned that we sometimes rely quite heavily on our simulation tools and sort of tools and skills. And this is a quite good example of that, I think. This is the propulsion motor for the new Hurtigruten exploration cruise vessels, that where the whole propulsion package here was delivered by Rolls-Royce Marine, now owned by Kongsberg. And where this blue machine you see on top here, that went from sort of data specification into actually introduction into the ship within 2 years, just sort of not stepping by any prototypes or scaled models or anything, just relying on the calculations. So this went into service last year, I think, and it ended up as a 3.5 megawatt machine with an efficiency of 98.6%. And to those of you who have been a bit into electrical machines, that is quite high. The normal here is probably approximately 97%. So actually that gain in efficiency of 1.6% is within a couple of years, just to fuel reduction in fuel consumption, is actually paying for the machine, and within the lifetime of the vessel, it's paying for the propulsion system or the propulsor. So that's a bit of history. This is what we're doing today. We are spending approximately 70% of our time on aviation, working very closely with a global team in Rolls-Royce, here in UK, US, Germany. So these are some of the projects that Rolls-Royce Electrical are into these days. The top one is ASL. It is a small general aviation aircraft, a sort of acrobatic aircraft that is on its way to making the world speed record for an all-electric airplane. And then in the middle there you can see the electrical vertical takeoff and landing aircraft concept that Rolls-Royce is developing. This is set up to transport up to 4 people in urban areas, and yeah, we're working to develop the propulsion system for that. And at the bottom here you can see EFAN-X, which is the world's largest hybrid electrical aircraft technology demonstrator. So it's a project that we're doing together with Airbus. It's actually a BA 146 that is rebuilt, so that one of the 4 jet engines has been exchanged with an electrical fan, and the motors or the electrical machines that are both doing the generation and propulsion for this are actually being designed using COMSOL. And have been designed in Trondheim together with a team in Derby, and has been built and is actually these days starting its test program in Trondheim, in Norway. So to finish off, I hope and think that this will be the starting of an era of sustainable aviation. Thank you.